Okay, hi guys. What I'm going to do is solve a relatively easy exact equation. But first, I'd like to go through the idea of the exact equation. Okay, and the idea is that you're trying to solve for some function with respect to x and y. And what they do is they just set this up to some constant. And then they say, well, if we take the total derivative of this function, then it will look like this. F sub x dx plus f sub y dy equals 0 because the derivative of a constant is just 0. Okay, and this is where you start. You typically, with these type of differential equations, you start here. Okay, with this total derivative. Sometimes they call it the exact derivative as well. And what they want you to do is they want you to find this statement here, your function, and set that equal to some constant c. Okay, and they'll say, the idea is if your function, if f is c2 or twice continuous, then their mixed partials, or its mixed partials, will equal each other. Okay, and that's how you know if your equation is exact. Okay, if it's twice continuous, then the mixed partials will be equal to each other, and I'll say, okay, this is perfect. This is an exact equation. Okay, so let me draw this again. If you have a function of which you're trying to find, this is your final answer will be, and you differentiate once to get the total derivative, and this is how they'll give you the question. Okay, so if you're here and you need to get up one level so that you can find the function, what you should do is you integrate either one of these. It doesn't really matter. You integrate one of them to give you the function up to a constant, up to some constant. If you integrate with respect to x, then your constant will not just be a normal constant. It'll be a constant that could have a y or could not have a y, which we need to eventually solve for. Okay. The idea is because if you're here and you take the derivative with respect to x, it will give you this, but in its derivative there will be no y terms that show up. So when you put this constant there, you don't just mark it as a c or a k like a normal number constant. You need a variable constant there. So you integrate this to bring you up one level, and then you differentiate. Once you're here, you have this function. You differentiate it with respect to y, so that let's see, you can set it equal to this guy right here, and then you can make the comparisons. So basically, you start here. You're given the function, and then you start here to get the function, and then you take its derivative to get you back down to this y. And when you make some comparisons here, you can figure out what g of y equals to something something. Okay, and then you can plug it into this guy right here. It will make more sense with more practice. But after that, after you find g of y, then it's very easy, and you can just plug it in and figure your function out. So let's do an example, and it will make more sense. Okay, so my example will be 2xy cubed plus 3x squared y squared dy dx, let that equal to 0. And this doesn't exactly look like the total differential just yet, so let's multiply everything by dx. 3x squared y squared dy equals 0. So remember, this part right here is your f sub x, xy. And what we want to do is, well, label this part 2. This part is your f sub y, and the way I keep them straight is that here we have a y, so this is f sub y dy. Here we have an x, so this is your function with respect, your function's derivative with respect to x. So let's check, are the mixed partials equal? If you take the derivative of f sub x with respect to y, you'll get 6x y squared. And if you take the derivative of f sub y with respect to x, you get the same thing, 6xy squared. So because these are equal, they are indeed exact. Okay, and that's your first step. Just check if the mixed partials are equal. Okay, likewise, your next step will be to go ahead and integrate f of x dx to get you to your function, what they say, your function up to a constant, that constant being with respect to y, because when you took the derivative, it only gave you your x terms. Any y's that were isolated or by themselves without an x went to 0, and so they didn't show up in your partial with respect to x. So to get those back, you don't just tack on a constant, but you need a variable constant with a y in it. Okay, so let's go ahead and do that. If we take the antiderivative of f sub x, in this case that was 2xy cubed dx, you'll get x squared y cubed, and like I said, plus your constant, your variable constant, and then we'll go back down a level. So we'll take its derivative, partial derivative with respect to y, x squared y cubed plus gy, and set that equal to what we know our the y's partial derivative in our total differential, which was 3x squared y squared. Okay, so the left side stays the same, 3x squared y squared, and that's the right side. The left side, if you take its partial derivative with respect to y, it will be 3x squared y squared plus g prime. Okay, therefore you get g prime of y equals 0. And if you need to actually find g of y, what does that equal? How can you get it? You integrate both sides with respect to y, and you get that g of y equals c, because the antiderivative of 0 is a constant. Okay, so what you do is you get this guy, and you plug them back here. Okay, therefore you get that your final answer should be f of xy is equal to x squared y cubed plus c. And you can box this answer. Okay. So that's your final answer, and just the more you practice, the more it will make sense, and being able to you start with the total differential, and you integrate, find that it's exact, integrate one of the pieces and then differentiate it to solve for your variable constant. Thanks for watching. Please leave a comment and check out any of my other differential equation videos.